introductions to mathematical statistics. So here we stop in our last video, and in our last video I tried to make a comment that there's an error here. So here it should be so here the probability of C1 intersection C2 is just 1, and there should be 1 over 4, and this should be 1 over 4. Then subtract this over 4, and then you have 1 minus 4, and there should be 3 over 4. This is our result. So today we will continue to define mutual exclusion, and then we'll move to equally likely then counting rules, and then with permutations, combinations, and then we'll check some exciting questions. Okay, so let's start. We have mutual exclusion. Exclusion. So definition. Two sets C1, C2 are called mutually disjoint if C1 intersects C2 equals to empty set, that is, there's not a common element in both two sets. So a sequence of set C1, C2 that are mutually disjoint if any two sets are mutually disjoint. Then let's check on that definition second too. So two events C1, C2 are called mutually exclusive if C1 intersects C2 is empty. Okay, so a sequence of events C1, C2 dots are mutually exclusive if any two events are mutually exclusive. So if the sample space fancy C or called the C and custom of Cn, then say the sequence is called associate. Then the sequence is called associative. So let's check some theorem here. Theorem if C1, C2 are mutually exclusive, then the probability of C1 union C2 will be equal to probability of C1 plus probability of C2. So there's no need of you subtracting their intersection, because their intersection will be 0. Okay, this will be 0. So then if they are mutually exclusive, then their probability of their union should be equal to probability of the individual events. And then probability of the countable union, in this case, should be equal to the summation of the probability of Cn n equals to 1 to infinity. Alright, so let's now move to another subtopic, which is equilikely cases. So let C1 dot Cn be a partition of our sample space C. So these guys are equally likely. If probability of C1 is equals to dot probability of Cn is equals to 1 over n. Okay, so let E equals to C1 union dot union Cn, and our R is less than or equals to n. So then the probability of E will be equals to R over n. Okay, and then here n is the total number is called the total number of ways in which the random experiment can terminate R. Terminate and R the number of ways that are favorable to the event E. So thus probability of E is equal to the number of ways favorable to the event E divided by the total number of ways in which the experiment can terminate. So a simple example is that you have 2 red balls, then you have 3 red balls. So the probability of balls and then let's say green. So probability of picking 1 red ball or any ball, probability of 1 probability 1 ball will be equal to the total number of probability we have, which is 5, and the total number of red ball we have, which is 2. So, but that is for undergrad. Then in order for us to handle some complicated probability, we have to define counting rules. Then in counting rule, the first counting we have is multiplication rule. So for multiplication rule, suppose we have two experiments. Okay, so the first experiment result in n1 outcomes, while the second experiment result in n2 outcomes. So the complete experiment there will be first experiment followed by second experiment so as n1 times n2 outcomes. Okay, so for example, it is straightforward. To extend the K experiment. Now if you have more than 2 experiments, simply a composite experiment of K's as n1 times n2 dot nk outcomes. So, and that is very easy for us to understand. Okay, so another counting rule we have is permutation. So a club has n individuals. Okay, and we have a goal, and the goal is to choose a committee of K members where each member has a different title. So e.g., we have a president, we have vice president, and we have treasurer, so that means that we have k position. So for church committee, church committee, we only have 3 space. Is the permutation of k members from n, and that will be p and k. So now if the same 3 persons are selected, permuted to receive different titles, each permuted result is counted as a distinct outcome. Okay, so how many church committees are there? So let's say for example, so if the same 3 persons are selected, so our permutation are permuted to receive different titles. So don't forget, this person cannot be a president, so that each permuted result is counted as a distinct. So that once we elect someone as a president, then we cannot elect another person as a president. So the other people can be elected as either treasurer or vice president. So the question is, how many church committee are there? And this is the major question that permutations tries to handle. So don't forget, for the first title, so we have n people to choose for that. To choose from. But now for the second title, the number of people to choose from will reduce, because you cannot choose someone as a president and also choose the same person as a treasurer. So we have n-1 person to choose from. So for the third person also, for the third title rather, so we have n-2 person to choose from. So dot. So if we have case title, for the case title, then we're going to have n minus k minus 1 person to choose from. Okay, so with that now, by multiplication rule, therefore by the multiplication rule, we can multiply everything together. The first person, we have n person to choose from. The second person, we have n-1. The third two, we have n-2. The last title, we have n-k plus 1 to choose from, and this goes to n factorial over n-k factorial, and that's the definition for permutation of and for k title. So lastly, we have what is called combination. Combinations. So in permutation, not in permutation we just did permutation of members, the order in which the committee is selected, does not matter. So all the members. So what matters in permutation? All the members matters. So for the example we did, so we just care who is in the committee and not necessarily the title. So and then we have 3 titles. So we don't care if the first person is the president, the vice president, or the treasurer. So we don't care about the order at which the committee is selected. So what we just care about is who the members are, and then we care about the committee and not necessarily the title. Okay. So but in combinations, we had to answer the questions that if the same group of k members are selected, in how many ways can they permute among themselves? So in other words, how many such combinations are there in our permutation? So now we didn't care. We want to see how many ways can we rearrange them, or how many ways can we in how many ways can we permute among themselves. So how many combinations? Let's put it this way: if the same group of k members are selected, so in how many ways can they permute among themselves? And then the question is k factorial, because we have k members. So this gives us the basic motivation for combination. So this permuted results are now counted as one combination. Okay, so the next question now is how many such combinations are there in the P and K permutations? And that results to the definition of combination. N combination k is now equals to permutation n of k over k factorial, and that gives us n factorial over k factorial bracket n minus k factorial. So let's check some basic example. So we have this. So we call this a poker problem. So let a card be drawn at random from an ordinary deck. Let me increase it. Of 52 cards, which has been well shuffled. So the sample space C is the union of n equals to 52 outcomes. So assume that each of these outcomes is equally likely so that it has the same probability of 1 over 52. So we have to find the probability of PEIs. So first, we say let E1 be the event of a flush. In other words, all 5 cards of the same suit. Then question 2, let E2 be the event of getting exactly 3 of a kind. Then the other 2 cards are distinct and are of different kinds. And question 3, let E3 be the event of outcomes in which exactly 3 cards are kings and exactly 2 cards are queens. Okay. So let's check the solution. So solution question 1. Don't forget in a poker's card, for those that know what a poker's card is, we have 4 flush, which we call which is just half of the same, which is of the same what will I call it now? The same the same style. You know, we have an heart, we have a diamond, we have an heart, we have spade, and then we have something of this one. So we have 4 kind of it. So we are saying let E1 be the event of a flush of all 5 cards have the same suit. So we have 4 suits, and then that 4 suits we are just want to pick 1 suit. Then from that 1 4 suit we have 13 number of individuals. Then we are going to pick out of this 13 we are picking 5. And then don't forget, out of 52 we just want to pick 5 cards, and that gives us the probability of E1. So let E1 be the event of a flush. So we have 4 flush, then we pick 1, then all 5 cards of the same suit. We have 13 suits, and then we pick 5 suits. Okay, and then if we solve this carefully, we have 4.1287 over 2598960, and that gives us 0.00198. Okay, so let's check question 2. Question 2, let E2 be the event of getting exactly 3 of a kind. 3 of a kind. So we have 30 kinds. So we pick the first kind, and don't forget we have 13 kinds. So we pick 1 out of this one. We pick 3 of the same. So let E2 be the event of getting exactly 3 of a kind. We have 13 kinds. We first of all pick 1 out of that 1 kind. We draw 3 out of those kinds. So that means that we have 3 kinds of the same. So then the other 2 cards are distinct and of different kinds. That means that if we pick 1 out of those 13 kinds we have, we'll be left with 12 kinds, and from that 12 kinds we want to pick 2. So we pick from those 2, we pick 4 of one kind and then 4 of the remaining parts, and that we have this result. and we solve this also. We have 0.0211. So lastly, question 3 is probability of eating. So question 3, a probability of E3. So here now, be the event of outcome in which exactly 3 cards are kings and we only have 4 kings. Out of the 4 kings, we pick 3. And exactly 2 cards are queen. We also have 4 queens, then we pick 2. And that gives us 52/5. And then if we also solve this, something 0.0000, that we have 2, 3, 4, we have like 4, 1, 2, 3, 4, 5, 3, 4, 5, 9, 3. So you can just try to Google search and see the poker's card in more clear picture. So, and that is where we are going to stop for today. Then in the next video we try to check additional properties of probability, and which will lead us to check some exercises. Let's just quickly do that, so that in the next video we will go straight to the exercises of question under this part we have covered in this video. Alright, so let's check addition. There's 1.32 additional properties of probability. And these additional properties are so wonderful. Let's check the theorem. If we have a sequence of Cn and it's an increasing sequence, of events, then this theorem will limit n tends to infinity probability of Cn is equal to probability of limit n tends to infinity Cn is equal to probability of the countable union. Okay. And then if it is decreasing, if our Cn is a decreasing sequence, of events, then limit n tends to infinity P of Cn equals to probability of limit n tends to infinity Cn, and that will be equal to probability of the intersection n equals to 1 infinity Cn. So then after that we have what's called bullish inequality. So we can let Cn be a sequence. We don't know if it is increasing or not. Then the probability of UCn of n is less than the probability of sum. So here we stop. So in our next video we check exercises and this question. Hope to see you.